So welcome back. So this video is going to talk about the grade 12 identities. We'll be talking about compound identities and double angle identities. And that's what comes next. Let's get started. So we'll be starting with compound identities. That comes next. Another identity that you need to learn is compound identities. Now, the concept of compound identities works in such a way that you have sine or you have cos, and in the bracket there is something plus or minus something, and you close the bracket. As far as you can fit in something in here and fit in something in here, it works as a compound identity. Now, one thing you also need to remember about compound identities, if you have sine A plus B, we do not say it is sine A plus sine B. This will be considered wrong. Now that we've talked about what compound identity isn't, let's actually write down the 4 compound identities you need to remember. These are the compound identities that you always need to remember. The compound identities involving sine, we normally have alternating sine cos. As you can see here, we have sine A cos B, and over here we have sine B cos A. Now, another thing to also remember is that whenever you have sine, if there is a positive here, you should have a positive in the identity. The same thing also applies here. If you have a negative here, you should also have a negative over there. So with cos, you would notice that you would have the cos's out of the way first of all, then you have the sines. As you can see, cos A, cos B. Then we have sine A, sine B, right? Another very important thing is the signs. Whenever you have a positive, the identity produced will be negative, and whenever you have a negative, the identity produced will be positive. You need to try as much as possible to memorize this. One thing you should also know is that identities doesn't necessarily always have to have A minus B. You could also create your A minus B. What I mean by that, if I have something like sine 5A, this can be written as sine 4A plus A. It could be written as 3A plus 2A, and so on and so forth. But the most important thing I need you to understand about this is that depending on the type of question you get, you will know what you can break it down into. This works a lot with special angles. So take for instance, if I have something like sine 75, and I want to put this in terms of compound identities, it can actually be written as sine 45 plus 30. Then this could be broken down into sine 45 cos 30 plus sine 30 cos 45. Now, if you look at this intently, you can actually see that this represents A, that represents B. We have sine A cos B. You also have sine B cos A. So this is exactly what you do with compound identities. Not every single question will look like the default over here. You might have to create your own compound identities. Now that you understand how compound identities work, let us try out an example so we can put most of this into practice. Let's get into it. So next up, we'll be trying out this example. This here says cos 59 times cos 346 plus sine 121 times cos 76. Now looking at this over here, we notice a couple of things. we are asked to simplify this. I think I didn't write that. We're asked to simplify. We want to simplify this whole thing over here. Now, let us start with the basics. From what we talked about in previous lesson in trig, whenever you have things greater than an acute angle, you always try to reduce it using your reduction formula. So we can reduce this because that is not an acute, and we could also reduce this because that is also not acute. So let's start with that right off the bat. So as you see, 346 is broken down into 360 minus 14, which makes that in your fourth quadrant. And 121 is broken down into 180 minus 59, which also makes that in your second quadrant. You can definitely see that this is cos 14 because cos is positive in the fourth quadrant, and this is sine 59 because sine is positive in the second quadrant. Now, in terms of our compound identities, the goal is to always have A and B, right? Plus or minus A and B. So now we need to break them down into possible A's and B's. So now if this is a compound identity, so we understand that 59 could be A and 14 could be B. So as you can see, and it also makes sense that this also will be A. So you can see 59 and 59, so that's a good A. Now the problem is that B here we have 14. Now in this case here we have 76. Now not only do we have 76, we have cos 76. This looks like the cos compound identity, which had cos, cos, then sine, sine. But this is sine cos. So we notice that we can actually change this using co-ratios. Now if you're wondering how I got this, this is just a step I kind of skipped, which is, so 76 we're written as 90 minus 14, which becomes sine 14. Now this looks exactly like we want, as you can see properly. That's A, that's B, that's A, and that's B. Now because we notice we have two cos, we have cos and cos, then we have sine and sine, we definitely know that this here would actually be cos. And we would also have A and B, so we will have 59 and would also have 14. Now to determine the sine, remember with cos, whenever you have a positive, it means that this here would be the opposite, which is a negative. So from this, we actually have this as cos 45. I'm breaking this down. This is root 2 of 2. And this is exactly how you can simplify using compound identities. Okay, so let us try out one other examples of compound identities. So we have this question over here. It says proof that sine 15 is equals to root 6 minus root 2 over 4. So like we said before, that we are also allowed to create our own compound identities. We understand that 15 could be rewritten as 45 minus 30. Could also be rewritten as 60 minus 45. Now if you're wondering why exactly am I choosing special angles, what you need to understand is that if I choose any other value that creates 15, it will be difficult for us to answer this question without using a calculator. But with special angles, like we talked about in previous lessons, we don't need a calculator to simplify questions like this. So I'm going to rewrite this as sine 45 minus 30. From compound identities, we understand that this here would be that's A, that's B, so therefore that's A, that's B, and that's B, and that's A. So the line you see over here is just me using special angles. For 45, for 30, I'm breaking them down into this. Then by simplifying the first part here, I multiply the root 2 times root 3 gives you root 6, 2 times 2 gives you 4. That's why we have this over here. And this here is 1 times root 2 gives you root 2, and 2 times 2 actually gives you 4. So this is wrong, sorry about that. So that is 4. There you go. Then with this, we can just use the concept of LCD. So this will just be 4 root 6 minus root 2. And that's your answer. So this is another example of how you can use compound identities. And that was compound identities. Now the second part of this video is going to be talking about double angle identity and how it works. Now we're going to talk about the explanation, then we'll also do some examples so you guys can understand it. So let's get into it. So the next thing we'll be talking about is double identities. So double identities, we also have double identities for sine, and we have double identities for cos. Now, sine is the easy one, so let's start with that. So we have sine 2a. So whenever you have 2 over there, you can rewrite it in that way. You have 2 with your angle, it can be written like this. This is the only double identities that you have for sine, and for cos. So for cos, however, you have 3 choices you can get. Whenever you have a double identity for cos, it could either be cos squared a minus sine squared a, or 2 cos squared a minus 1, or 1 minus 2 sine squared a. Now, you might be wondering, which one do I choose for a particular question or a particular problem? I normally say, when in doubt, try as much as possible to choose this one. If you don't really know what to do, use this one. Now, if you have questions that involves cos in there, where the majority of the questions has cos in there, you are best served by using this. If you have majority of the question that has sine in there, or you notice that you actually need sine, right? You are missing sine, but you notice that you can work with sine, try as much as possible to use this. If you see that there's a mixture of sine and cos and you're not 100% sure which one to choose, definitely choose the first one that we have over here. That's exactly what I recommend whenever you use double identities. Okay. Now, one thing about double identities you also need to know is double identities could also be written in multiple ways. With double identities, you do not expect it to always look like this, which is cos 2a. It could look like cos 50, whereby it can be rewritten as cos 225. You can break it down into maybe something like this. It could look like this, whereby this can actually be rewritten as. So one thing that comes to mind whenever you have questions that involves double identity is that with double identities, it doesn't necessarily always have to look like this. However, whenever you notice there is an even number and there's a possibility of bringing out a 2, you can actually, like in the case of 50 and 4a, you can actually bring out a 2, then use your double identities like you've learned. Now, there are rare cases whereby they would not be even number, but you could also use double identity. So you have maybe a number like this. Now this can actually be rewritten as, because if you think about it, 2 times 33 over 2 also gives you 33, and the answer would be, yeah, another example. This can be written as, which would be, yeah. So this is exactly how it works if you notice that you have odd numbers, whereby you can rewrite it as a fraction. So this is exactly how double identities actually work. It only works for sine and cos. If you need it to work for 10, you have to convert it to sine over cos. That's it. So this is exactly how you use your double identities. Now that we have the basics of double angle identities out of the way, let us try out a question whereby we have to use what we learned in double angles identities to solve the question. So we're going to be trying out this question here. It asks us to prove that 1 minus cos 2 theta over sine 2 theta is equals to tan theta. In this case here, it will be recommended to prove the left hand side is equals to the right hand side because we have more information over here. So as you can see, we have a double identity in the numerator. With the denominator, it is straightforward. We have no problem with that. However, with the numerator, we need to look at what we actually require. Now, we notice that we are trying to prove tan theta, and tan theta is the same thing as sine over cos. So it means that in our numerator, we want sine. So I'm going to change that accordingly. So I'm going to write so as you can see, we changed the cos 2 theta into this because in the numerator, getting the sine would serve us well. So we want more sine than cos. Simplifying this would give you which is the same thing as I'm changing this sine squared theta into 2 sine theta is because I understand that me writing this would allow me to cross cancel properly. So cross cancelling, I see that 2 will cancel 2 out, sine theta will cancel sine theta out, and therefore all I'm left with is sine theta over cos theta, which as you know gives you tan theta, and that is exactly what they told us to prove over there. Let's try out one more example in double angle identity. For our final example, let us try out a question which combines double angle and compound identities together to solve a question. Are you guys ready? So now we are asked to simplify sine 36 over sine 12 minus cos 36 over cos 12. Now, whenever you're simplifying trig, at the back of your mind, you should always think algebra. And one of the basics of algebra is that whenever you have fractions, you get your LCD. So if I have A over B minus C over D, I understand that the first thing I do is that I get LCD. In this case here, it is BD. Then I can write everything in a big fraction like that. Okay, so that's what comes to my mind whenever I see fractions in algebra. I need to replicate that in trig questions. So I see this, the first thing I do is that I have my LCD. The LCD for this would be sine 12 cos 12. So as you can see, your numerator would be sine 36 cos 12 minus sine 12 cos 36. Now, one thing I also notice automatically here again is that this is A and that is B, and this is B and that is A. And I also see I have sine cos, sine cos. So that's definitely a compound identity that we talked about. So this would be written as 36 and 12. Now, because it's negative here for sine, the sign doesn't change. You have a negative over there. And that is over. So therefore, simplifying this would give you. Now, looking at 24, I actually see that 24 is double 12. So it reminds me that I could actually use double identities to simplify this a little bit, which is this. Sine 212 would be and as you can see, we can also cross cancel again. Sine 12 can cancel sine 12 out. Cos 12 can cancel cos 12 out. So all we're just left with would be 2. And this is an example whereby we actually combined our double identities and our compound identities to answer the question. And it was based on the backbone of LCD. So whenever you have fractions in trig, try as much as possible to think of LCD and combine your fractions. And that's exactly what we did. And that's it. This is exactly what you guys need to know about compound and double angle identities. The next video will be talking about trig equations next. We'll be looking at how to use general solutions and all those kind of nice stuff. You can check out the descriptions for other videos on trig. You can also check out the descriptions for other videos that we've covered on other sections in maths. On your way out, please do not forget to like and subscribe. Thank you.